Assessment of wind potential in the perspective of water pumping in Sahelian area of Burkina Faso. Abstract. This paper focuses on the prospects for wind pumping installations in the Sahelian and Sudano-Sahelian zones of Burkina Faso. 3 localities were chosen for the study, namely, Dori, Ouahigouya and Ouagadougou. A statistical study allowed the determination of average wind speed. Wind speed average at the height of the tower on the 3 sites varies between 2.4 and 4.2 m/s. The availability of groundwater resources in the Sahel, combined with the wind regime, makes it possible to determine the prospects of installing a pumping wind turbine at each site. Usable outout power of chosen wind turbine calculation made it possible to determine daily flows drawn off, using a mechanical pumping wind turbine and an aerogenerator of different nominal powers, depending on the total manometric height. The advantages and disadvantages of each pumping system are highlighted. The results show that Ouahigouyas and Ouagadougous sites are suitable for such installations, while Dori's site requires hybrid systems such as solar photovoltaic/wind or solar photovoltaic/generator. Keywords: livestock watering, wind energy potential, pumping wind turbine, total manometric height, rate of flow. 1. Introduction. In recent decades, marked by droughts in Sahelian countries, many pastoralists have relentlessly moved in search of water and pasture. In Burkina Faso, pastoralists and their livestock leave the Sahelian zone, considered to be the first breeding region of the country, and migrate to agricultural areas in the south, especially during the hottest months of the year. 1. The overcrowding of farm animals in the reception areas creates conflicts between farmers and herders. Furthermore, livestock occupies a strategic place in the economy of Burkina Faso. According to the Ministry of Animal Resources of Burkina Faso, livestock contributes 10% to the gross domestic product and occupies the second place in value of exports after cotton. Animal husbandry is a source of income for more than 80% of the population too. Given the importance of the livestock sector in the national economy and social conflicts created by the migration of livestock to agricultural areas, there is an increasing urgency to address the issue of livestock water supply in the Sahel of Burkina Faso. Field surveys show that the total demand for water for watering large herds of livestock in Burkina Faso Sahel is estimated at 72 million cubic meters per year. 3. Watering livestock with surface water is the method most used by breeders. 4. Because of the significant potential evapotranspiration in the Sahel, surface waters of the last rainy season are quickly evaporated. In addition, Burkina Faso Sahel groundwater resources map shows that the chosen sites are characterized by the abundance of groundwater, with a tank roof ranging from 10 to 100 meters deep. 5. Several attempts have been made to make water available in the Sahel of Burkina Faso in dry season. Christine drilling, which pump is powered by a generator, allows several hundred animals and people to access drinking water, precious and scarce during non-rainy periods. 6. However, this pumping system has experienced technical breakdowns resulting in its inoperability. Solar, wind and biomass energy potentials in the Sahelian zone show that it is favorable to renewable energy systems. Solar energy is mainly used in photovoltaic pumping systems for supply drinking water and for small-scale irrigation. 7. Biomass and wind energy are not exploited. Wind energy has experienced very strong growth over the past decade, thanks to technology's development and benefits for environment. 8. Among possibilities for harnessing wind energy, there is water dewatering. Technical choice for a type of wind pumping installation on landlocked sites and distant, mainly in Sahelian and Sudano-Sahelian zones, depends on parameters such as site wind potential, water need, water point nature and distance from wind turbine to place where water should be brought. 9, 10. The main objective of this article is feasibility study of wind pumping system installation on 3 sites in Sahelian zone of Burkina Faso, allowing to permanently supply water to breeders and their herds. 2. Material and method. For wind regime and the pumping rate study, year is divided into 3 periods depending on climatic specificities: dry and hot period, from March to June, rainy period from July to October, and harmattan period from November to February. Study is conducted for 4 months, March, April, May, and June, representing dry and hot periods, during which water need is highest and surface water is completely evaporated. Wind potential assessment. For wind potential assessment, it is necessary to express wind speed frequency distribution on the site 11. Weibull distribution is the most widely used and recommended in literature for expressing wind speed frequency distribution 12. In Weibull distribution, wind speed variations are characterized by two functions, probability density function and cumulative distribution function 13. Probability density function f, v, indicates time fraction, or probability, for which wind have the speed v. It is given by equation 1. Where c is scale factor, m/s, k is form factor, without unit, is wind speed. V. Cumulative distribution function gives time fraction, or probability, for which wind speed is less than or equal to speed. Corresponding cumulative frequency is given by equation 2. V. Weibull parameters estimation. There are several methods for estimating Weibull law parameters from raw wind speed data during a given period. But, power density method is the most accurate method for windy sites like those in this study 14. Energy pattern factor EPF is defined by equation 3. Where is the average wind speed, and intervals number. V. Parameter K value is determined using. According to equation 4. Then C is determined with equation 5. Where is the gamma function defined by equation 6. Average wind speed. According to Weibull distribution, average wind speed is calculated with equation 7. V. Where V is wind speed rated, F, V, occurrence frequency. Wind rose. A wind rose allows to know, for a given point, wind frequencies observation, according to direction and force criteria 15. Wind direction is wind origin. Wind's origin is determined according to following directions: between 0 degrees and 90 degrees, winds come from northeast, NE, between 90 degrees and 180 degrees, winds come from southeast, SE, between 180 degrees and 270 degrees, winds come from southwest, SO, between 270 degrees and 360 degrees, winds come from northwest, NO. Wind speed vertical extrapolation. Wind speed data for the study are measured at 10 meters above ground. It is necessary to estimate Weibull parameters and wind speed at different altitudes 16. Weibull parameters extrapolation is obtained by equations 8, 9, and 1. Where K0 is shape parameter at measurements height, K1 shape parameter at wind turbine hub height, C0 scale parameter at measurements height, C1 scale parameter at wind turbine hub height, Z0 measured height, 10 m, Z wind turbine hub height. Wind speed extrapolation for different altitudes is obtained with equations 11 and 12, 16. Where V is estimated velocity at height Z, V0 wind speed at measured height, Z wind turbine hub height, Z0 measured height, AJ empirical factor expressing surface roughness influences and atmospheric stability, ZG geometric mean height and R0 soil roughness. In present study, wind speed measurements are carried out in airports and ground roughness is rural type, R0 equals 0,07 m17. Wind available power density. Wind power density represents the amount of energy produced by wind. Power density available in wind, POV, per area unit swept by wind turbine blades is given by expression 13, 18. W/m2, 13, dot plus dot equals 0321 dVVFV POV. Where is air density, kg/m3, is wind speed, probability density function. VF. Wind recoverable power density. According to Betz limit, the maximum wind recoverable power density, PREC, on a site becomes equal to 16/27 of available power density. Equation 14 translates this relation 18. W/M2 14 dispor CPP 2716 equals wind recoverable energy per area unit and for 1 year, according to Bed's limit is expressed by equation 15. Kilowatt-hour/M2. 15 Rec PE 76,8 equals wind turbine average power supplied. Power provided by a wind turbine, PU, is given by equations 16 and 17, 18. 16 plus 00 and KLB. Poor. With K-stat kraton VVPV equals where V start is starting speed, VRAT is rated speed, V stop is machine stop speed and PN is nominal power. Electrical output power average, PEL, is given by expressions 18 to 20. Where V start is starting speed, VRAT is rated speed, V stop is machine stop speed and PN is the nominal power. FC is factor form given by equation 21. Usable wind power. Useful power average is related to electrical output power PEL by a ratio expressing transformation efficiency. Considering aerogenerator efficiency, usable wind power average PU is given by equation 22. Wind turbine efficiency is given by equations 23 and 24. With where FIO is aerogenerator the vehicle power, PN aerogenerator nominal power, air density, S wind turbine blade surface. Pump flow estimation. Two pumping systems are discussed in this study, namely, wind turbine mechanical pumping and wind turbine electric pumping. Mechanical pumping. Considering a mechanical pumping system of overall efficiency and total head of height HMT, daily flow QD is given by equation 25. Where HMT is total manometric height, G gravity acceleration, water density. Pumping system overall efficiency, and mechanical power provided by wind. Electric pumping. Considering an electric pumping system of overall efficiency and total manometric height HMT, daily pumped water flow QJ is given by equation 26, 19. HMT is total manometric height, G gravity acceleration, water density. Pumping system overall efficiency and PEL electrical power. Studied sites choice. Feasibility study covers Dori site in northeast, Ouahigouya site in northwest and Ouagadougou site in central Burkina Faso. All sites are located in Sahelian zone of Burkina Faso, whose hot and dry climate from March to June, rainy from July to October and cold and dry from November to February is characterized by long periods of drought. In Sahel, rainfall is erratic, lasts only about 3 months and average annual rainfall is between 300 and 600 mm. Rain's poor distribution in this area has resulted in increased water requirements for livestock. Table 1 gives sites geographic coordinates. Data used in this study are provided by Burkina Faso National Directorate of Meteorology 20. These are results of tri-hour observations of wind force, FF_XX, and direction, DD_XX, from 0 to 24 hours and 10 meters above ground level, from the weather station of 3 sites, Table 1. They correspond to a collection period of 10 years, from 2004 to 2013. Data recordings are made daily, 3 hours apart, for a total of 29,224 measurements collected over 10 years, 2004 to 2013, for each site. Pumping machines choice. Wind energy exploitation principle in water pumping is based on kinetic energy transformation contains into mechanical energy, once in contact with wind machine blades. For electrical pumping, mechanical energy is converted into electrical energy by alternator which supplies motor pump system installed in well. Used pump is usually centrifugal pump with a synchronous motor, which operates at variable power and speed 21. For mechanical wind pumping, mechanical energy activates piston pump via connecting rod, mounted on rotor shaft, which converts rotary motion into reciprocating rectilinear motion, which controls the piston pump installed in well 22. Starting speeds of mechanical wind turbines are order of 2.5 to 3 m/s. Converter pump efficiency is order of 60% 23. These wind turbines are generally equipped with propeller and whose diameters can reach 9 meters. However, because of mechanical stress, stem cannot exceed heights of 20 meters. This type of installation is reserved for wells whose depth is less than 15 meters 23. 3 Results and discussions. Figure 1 shows wind speed measured distribution at Dori, Ouahigouya and Ouagadougou sites. Figure 1. Wind speed distribution at the 3 sites. Observation in Figure 1 is that calm winds, speed less than 1 m/s, are frequent on 3 sites. Calm winds frequency is 0.35 for Dori site, 0.20 for Ouahigouya site and 0.15 for Ouagadougou site. Considering the frequency of calm winds, Ouagadougou site has the best wind distribution among 3 studied sites. Variable's distribution shows that studied sites are not enough windy. Table 2 shows variable shape and scale parameters monthly variation, estimated by power density method, for studied sites. Observation is that shape parameter K varies between 1.038 in Dori, in March, and 1.8932 in Ouagadougou, in April. So, wind speed is more uniform in Ouagadougou during April month, while it is less uniform in Dori during March month. Scale parameter C varies between 1.8432 m/s in Dori, in March, and 5.0467 m/s in Ouahigouya, in June, which shows that Ouahigouya site is windiest for this period. Monthly wind speeds average at 10 m height at 3 sites are shown in Figure 2. Figure 2. Monthly wind speed average at 10 m height at 3 sites. Wind speed has 4.63 m/s maximum value in Ouahigouya site, in June, while minimum wind speed of 1.26 m/s is recorded in November in Dori site. For Dori site, monthly wind speed averages are below 2.5 m/s. Ouagadougou site presents practically constant monthly speed averages, around 3.5 m/s. At Ouahigouya site, monthly speeds averages vary from 2.20 m/s in November to 4.63 m/s in June. Studied sites are not sufficiently windy. Wind roses. Wind roses at Dori, Ouahigouya and Ouagadougou sites are shown in Figure 3. C. Figure 3. Wind roses at 3 studies sites, A. At Dori site, B. At Ouahigouya site, C. At Ouagadougou site. Wind statistics observation and analysis show predominance in direction, northeast, with an inclination to north of geometric angle in third sector, between 60 degrees and 90 degrees, for Dori's site, southeast, with an inclination to north of geometric angle varying between 5th and 6th sector, between 120 degrees and 180 degrees, for Ouagadougou's site, southwest, with an inclination to north of geometric angle being in 9th sector, between 240 degrees and 270 degrees, for Ouahigouya's site. Annual speed averages are evaluated at 10 m to 130 m heights in 10 m steps, with soil roughness R0 equals 0.07 m. Figure 4 shows extrapolated wind speeds. Figure 4. Annual average wind speed at different height at 3 sites. We notice that at 60 m height, minimum annual average wind speed of 3.29 m/s is recorded at Dori, while average annual maximum speed of 5.54 m/s is recorded in Ouagadougou. Annual speed average in Ouahigouya is 5.25 m/s. At 130 m height, wind speed annual minimum average of 4.20 m/s is recorded at Dori, while speed annual maximum average of 6.76 m/s is recorded in Ouagadougou. Wind speed annual average in Ouahigouya is 6.39 m/s. From 60 m height, Ouagadougou and Ouahigouya sites have wind speed average higher than 5 m/s, which is sufficient for interesting electricity production with wind turbines. But for Dori site, it is necessary to go beyond 130 m height to obtain wind speeds greater than 5 m/s. Figure 5 shows recoverable power density at 3 studied sites. Figure 5. Recoverable wind power density at 3 study sites. 3 commercial wind turbines of nominal power equal to 3.5, 10, and 35 kilowatts were chosen for the simulation of electric pumping. Figure 6 represents useful and usable power for 10 kilowatts wind turbine, respectively at Dori, Ouahigouya, and Ouagadougou sites. Figure 6. Useful and usable power of wind turbine at 3 study sites. Water flow rates pumped by aerogenerator vary according to 3 sites and periods of year. Factors influencing water flow are highlighted in results summarized in tables 3 to 5, respectively for Dori, Ouahigouya, and Ouagadougou sites. Table 3. Pumping rates variation according to influencing factors at Dori site. Tables 3, 4, and 5 results analysis shows site influence. We notice that for same period, same total manometric height and wind turbine tower height, daily flows obtained at Dori site for June month, 0.0225 cubic meters, are low, compared to those obtained at Ouahigouya and Ouagadougou sites, which are respectively 2.70 cubic meters and 1.05 cubic meters. This is explained by low wind potential at first site. We note that, for Ouahigouya and Ouagadougou sites, water volumes pumped in June, with different total manometric heights and various wind tower heights, are always high compared to those obtained in other months. This is explained by daily wind speeds average levels observed during June month of each year on these sites. For Dori site, May is month with the highest water pumped volumes compared to those obtained in other months. Total manometric heights increase negatively affects water volumes pumped, whatever site and wind turbine height. Figure 7 illustrates well-pumped flows decrease curves, according to total manometric height, corresponding to hottest periods of year, from March to June at 3 sites. As an indication, for Ouahigouya site, in June, daily flow which was 2.70 cubic meters, for 20 minutes total manometric height, drops to 0.55 cubic meters, when manometric height increases by 10 m. Generally, wind turbines have various heights of pylon. For selected wind turbine for this study, it can be mounted at 3 different pylon heights, 20 m, 25 m, or 30 m. Pylon height influence is highlighted by tables 3, 4 and 5 results. By setting total manometric height at 3 sites, we see that increasing wind turbine pylon height translates into increase in water flows pumped. For example, for Ouagadougou site, with 20 m total manometric height and 20 m elevation of machine propeller, flow is 0.96 cubic meters in May, whereas it increases to 1.315 cubic meters, when height becomes 30 m, or 27% gain in flow for 10 minutes difference in height. Mechanical pumping simulation is done with machines of similar power to wind turbines used in electric mode. Simulation results with a 10 kilowatts power wind turbine, during hot season, from March to June are shown in figures 8. Different curves examination shows that pumped flows are more important in mechanical mode than by electric mode. But well depth constraints of less than 35 m, penalize the mechanical pumping mode. Pumped flows with large wind turbines are more important and offer great possibilities. However, the wind regimes on studied sites mean that, to obtain pumped water flows comparable to those of mechanical mode, it would require large wind turbines, for tower heights up to 130 m. For conclusion, wind energy potential study on installation sites went through wind data statistical processing, which allowed available wind potential assessment. Really usable wind potential was used to estimate daily flow rates pumped for several total manometric height. For electric pumping, daily flow average estimation, according to total manometric height pumping, was carried out considering 3 commercial wind turbines characteristics, supposedly installed on 3 Sahelian sites, namely, Dori, Ouahigouya and Ouagadougou. Results showed that, across all 3 sites studied, water flows pumped in electric mode are low, compared to livestock water requirement. Same study was made considering mechanical pumping mode and taking into account limits of system. It has been observed that pumped water flows are greater in mechanical mode than in electric mode. Ouahigouya and Ouagadougou sites can well house wind pumping installations. However, for Dori site, wind pumping is not efficient. For Dori site, we recommend use of other renewable energies in combination with wind energy, such as photovoltaic solar energy and biogas produced from livestock waste, used as gaseous fuel in generators. Similarity of studied problem in several areas of Burkina Faso, require that solution approach developed, be applied to all farming areas of Burkina Faso and in Africa's Sahelian area. 5 Acknowledgements. The authors want to thank the University Natsi Boni and the University of Lomé for providing enabling environment during the research.